We've talked about circuits in previous videos that included passive RC filters, but haven't directly looked at the circuit theory of these filters, or at how they behave in the frequency domain. In this video, we'll walk through some physics of these circuits and demonstrate their behavior on a breadboard. We'll also look at some simple active filter circuits with a common operational amplifier. Let's begin with a simple RC circuit. We'll have two nodes that correspond to an input and two nodes that correspond to an output. And we'll connect a capacitor and a resistor like this. Let's think about how this circuit will respond when the input is an alternating current. When the frequency is very low for that alternating current, in fact close to zero frequency, in other words DC, this capacitor will block the DC components and no current will flow through the circuit. When the frequency is very high, this capacitor will look like a short circuit and the current will be able to pass through. So if we think in terms of a gain, we define the gain now as the output voltage divided by the input voltage, we see that the gain of this circuit will depend on the frequency. And at low frequency, the C presents a very high reactance, so the output will be small. But at higher frequencies, the capacitor is essentially a short, and the output will be very nearly what the input voltage is. Another way to say this is low frequencies are attenuated in this circuit, whereas high frequencies pass through with very low loss. Or in other words, we have a high pass filter with a gain in the high frequency range tending towards 1. So I should just say that here and in the rest of the video we're speaking in terms of the angular frequency omega, which is related to the frequency that most of us know and love, the cyclic frequency, by a factor of 2 pi. So that's a simple physical picture of this circuit, but of course we can make it a little bit more detailed by looking at the circuit theory. Again, let's look at this circuit where we've got a V1, which is a function of time input, and we want to know what the V2 as a function of time output is. Well, there'll be a current I that flows through this circuit with elements of capacitance and resistance. And when we think about the AC theory of this circuit, that capacitor just looks like a resistor, but of course it isn't. It's a reactance, and it's capacitive reactance. And we know that the formula for the capacitive reactance is just 1 over j omega c, where j is the square root of minus 1. So we can apply Ohm's law to this circuit, and we know that the voltage drop from this node to ground is just going to be I times x sub c plus I times r, like this. But we also know that the voltage dropped across this resistor is just I, the current, times the resistance itself. So now we have an expression for V1 and V2, so we can write the gain as the ratio of V2 to V1. And that math looks like this. We have IR over I times the quantity 1 over JC plus R. And just doing a little bit of algebra on that, we can express that as j omega RC over 1 plus j omega RC. Now this really isn't satisfactory for being a physical measurable quantity because this is complex. In order to make this real, we take the complex conjugate and we multiply it by itself, so V2 times V2 star, where the star denotes complex conjugation. And we divide it by V1, V1 star, and then we take the square root of that. And so this is a way of taking the absolute magnitude of V2 over V1. Well, when we do that, there's a little bit of algebra involved, but we come out with an expression of omega RC over the square root of 1 plus omega squared R squared C squared. And when you look at this, when omega is really, really small, that this goes away and we're just left with this gain being essentially omega RC. So for very low frequencies, the gain of this circuit is proportional to the frequency. But when omega is really, really large, we see that this term dominates the denominator. When you take the square root, you just end up with omega RC, but omega RC is then just divided by that, so the gain tends to 1. So we can see now that this is a high-pass filter because we show that the gain is unity when omega is very high, and that as omega goes to 0, the gain also goes to 0. Well, the usual way of plotting this is in this sort of a plot where we have the logarithm of the frequency on the horizontal axis, and we take the logarithm of the gain, so log of the absolute value of V2 over V1. And when you do that, you end up with a shoulder at low frequencies, and then it gets to be 0 dB, or in other words, a gain of 1 as the frequency gets higher. And I think you can see that the breakpoint here, the omega sub breakpoint, is just when the gain is equal to 1 over the square root of 2, or 0.707. Right, you can see that where if you let omega equal 1 over RC, then this term becomes 1, this term becomes 1 in the numerator, so you end up with 1 over the square root of 2. Okay? Now, it might be good to review the dB notation just briefly. I never find it a terribly intuitive way to think in terms of physical measurements about. But if we just kind of go back and review this, the power gain is oftentimes expressed in units of dB. And this is the definition. So we have a ratio of 2 powers, P2 an output and P1 an input. If we take 10 log base 10 of that, then that's the ratio of those 2 powers expressed in dB. Now, we're not talking about powers in this video, we're talking about voltages, but of course we know that the power and the voltage are related to one another. And in fact, the power is equal to the voltage squared divided by the resistance. In this case, we're talking about impedances because we've got reactive components in there. And if the impedance levels are the same at the input of the output, then we can express this we can express our gain in terms of dB. The way we do that is we start with the definition of dB, 10 log base 10 of P2 to P1. But then the resistances, or the impedances, will divide out when we express the power in terms of the voltage. So we're left with 10 log base 10 of V2 over V1 squared. One of the properties of logarithms is that powers in the argument of the logarithm come down out in front. And so when you do that, you bring down a factor of 2 that multiplies this factor of 10. And that's where this factor of 20 comes from. So when we express things in dB, express the gain in terms of dB, we have a factor of 20 log base 10 of the output voltage divided by the input voltage. And so you can see that the power gain of 20 dB is the same as an output power being 100 times the input power. How can you see that? Well, if you have this this power being 100 times P1, then this is 10 log base 10 of 100, or log base 10 of 10 to the 2. That 2 comes down out in front, and you end up with 20 log base 10 of 10. Log base 10 of 10 is 1. All right, well, you can make yourself crazy doing these sorts of manipulations. But in the case of the voltage here, we can see that when this ratio is 100, we get a dB of plus 40 gain. When we go down in order of magnitude, we have the gain as 10. That's the same as 20 dB. When the gain is 1, that's 0 dB because the logarithm base 10 of 1 is just 0. And then it goes, in the opposite direction. When we have 1/10 or 0.1, then we have negative 20 dB. When we have 1/100th or 0.01, we have negative 40 dB, and so on. pretty easy to remember these even powers of 10, but when you have ratios that aren't powers of 10, somehow I at least am never able to internalize that. So you have to just kind of do this a lot and memorize some of these values. For a ratio of 2, that's a dB of +6 gain. When you have square root of 2 as your gain, then that's +3 dB. And then, if you take the inverse of it, just like we did over here, 1 over the square root of 2, or 0.707, is -3 dB. 1/2, or 0.5, is -6 dB, and so on and so forth. Okay, so the upshot of all that is that because at low frequency the gain is proportional to omega, we have a roll-off at low frequencies that is about 20 dB for every power of 10 decrease in the frequency. And the way we say that is that's a 20 dB per decade roll-off. All right, well, let's move on, and now instead of measuring the output of that circuit across the resistor, now let's measure the output across the capacitor. So just as before, we have a time variant voltage V1 in, and we want to know what the ratio of the output voltage is to the input voltage. So again, we just kind of follow our noses. We have V2 over V1, and very much as we did before, we can write V2 as the voltage dropped over this capacitor, which is by Ohm's law just I times X sub C. Then we have the voltage dropped through the entire circuit is just I times the resistive component plus I times the reactive component. And when you do the algebra for that, you end up with the V2 to V1 is 1 over 1 plus j omega RC. And when you take the absolute magnitude of that, then you end up with just the modulus. So it'll be 1 over square root of 1 plus omega squared r squared c squared. Now we can do the sort of limiting behavior just as we did before. When omega gets very, very small, you see now that this term goes away, and we're just left with 1 over the square root of 1. So the gain goes to 1 for very low frequencies. For very high frequencies, see that the gain goes to 0, because you just end up with 1 over something really big, which gets really small. And this is a low-pass filter, because at low frequencies you pass everything, you have a unit gain, and at high frequencies you pass nothing, you have 0 gain. And so, again, the usual way of plotting this, of log of the gain versus log of the frequency, is just the opposite of what we had before. We have, at low frequencies we have near unity, near, gain of 1, and then it rolls off, and again at a 20 dB per decade roll off in frequency. All right, well, let's look at how this works on the actual breadboard. And the first resistor and capacitors that I grabbed when I went to the junk box was a resistor of 100K, 100 kilo ohms, and a capacitor of 0.01 microfarad. And so when you compute the shoulder frequency here, you end up with 1 over 2 pi RC, and that comes out to be 159 hertz, which I just rounded up to 160 hertz. I've set this up to sweep frequencies, and I've started off at the low end frequency of 1 hertz, so getting as close to DC as I can. And I've got a stop frequency of 600 hertz. So if I sweep through this range, I should see a really nice effect in terms of roll-off frequency. And what I've done is I've taken the sync out of this function generator, and I've used that to trigger an oscilloscope. So in this shot, what we have is this yellow trace, and what I've done is I've adjusted the sweep time of the signal from the function generator in such a way that this corresponds to 1 complete cycle of the frequency sweep. You can see that if I just move this window over a bit, that would be this one here. So you can see there I'm starting a new cycle, and if I move it the other way, you can see there's the old cycle ending. I always want to go back. For some reason, I want that adjustment to be here. Alright, so this is as close to DC as I can possibly get. This is 1 Hertz, and this is the upper frequency, 600 Hertz of my sweep. So that means that this point here, in this direction right here, should be 350 Hertz, and so the waves down in here are going to be, close to 1. This is going to be approximately 350 Hertz cycle, and up in here we're going to have 600 Hertz cycle. And this now, this blue trace, is just the output across the resistor. You can see that up here I'm passing my frequencies, but as I increase in frequency, the amplitude of this response, that is to say V2, decreases. You can, of course, string these circuits together, and if you do that, let's just go down and look at how I've done this on the breadboard. So here is my circuit. I've got my signal in, signal out, resistor, and here is capacitor. So this is one complete circuit. But of course I can cascade these things. I can put that into another RC circuit. So here's same resistance and same capacitance, and if I measure the output of that, then I should see a further attenuation in frequency. I should actually see, if I string those together, not a 20 dB per decade roll-off, but actually a 40 dB per decade roll-off. Well, let's put that on, and the vertical scale is the same for both the blue and the purple trace. It's 500 millivolts per division. And in fact, you can see that down here for low frequencies, I have, essentially the blue and the purple trace are of the same amplitude. But as I increase in frequency, as I get closer to 600 Hertz, you see that the purple wave does in fact roll off much more rapidly than the blue wave. And that's exactly as we would expect. Now suppose we introduce an operational amplifier on the output of the RC circuit. That way we can increase the gain of the overall circuit. To demonstrate, here's what we're going to do. We're going to take this low-pass RC circuit, and we're going to feed it into a non-inverting op-amp. And if you remember that the gain of this non-inverting op-amp is just 1 plus the ratio of these two resistors, R3 to R2. And if we do that, we can then see that we have this gain that becomes 1 over 1 plus omega squared R squared C squared times the quantity of 1 plus R3 over R2. So if we make this operational amplifier a high gain circuit, then we can really increase the total output of the circuit. And to demonstrate that, we're going to take a resistor R3 to be 100 kiloohms and R2 to be 10 kiloohms, so that the ratio of these two is just 10, and that then will make this 1 plus R3 over R2 an effective 11 gain. All right. So we're just going to put this on the breadboard here. We're going to move the probe from the second pole of our RC filter over to the output of this. And let's zoom in on the oscilloscope here. All right. Let's turn on channel 3. It's already on. And it looks like we don't have a purple trace until you realize that the purple trace and the blue trace are the same volts per division, half a volt, 500 millivolts. So let's change that. And if this is a gain of a little over 10, then I would expect that as I change the volts per division to go from 500 millivolts to 5 volts, a factor of 10, that I should see the blue and the purple traces overlap. And in fact, that's pretty much what you see. Every now and then you see the blue wink out, kind of wink at you, and that's because it's not exactly a factor of 10, it's a factor of 11. But again, you see that we have the same frequency trend in roll-off, that the high frequencies get attenuated increasingly. But this is 5 volts per division versus the half a volt per division. So this purple trace is actually much, much higher in amplitude, in output amplitude, than the input. Of course, you can pick your own favorite op-amp circuit, inverting versus non-inverting, and your own favorite op-amp for that matter, to make your own active filters and derive the gain expression in ways very similar to what we did above. There are a few things you have to watch out for if you want to apply these ideas at radio frequencies. For example, op-amps have a bandwidth parameter known as the bandwidth gain product, which limits the maximum frequency and gain you can employ for a given op-amp. I'll link in some information below. We might revisit this in a future project and video. I hope you found this video interesting. If so, please give it a thumbs up below. Thanks for watching.